Hi everyone, we're continuing with section 3.2 on log functions and their graphs. So before, we talked about common logs, log base 10 of x, and natural logs, log base e of x. But let's talk about logs in general. What are some properties that logs of various types have in general? What are the properties of logs? All right, so I'll need to be careful here. We're going to play peekaboo. All right, let's talk about properties of logs. All right, basic log properties. Now we're going to assume that b is any nice base. Remember, a nice base is a positive number that's not 1. So we actually get an exponential function and a corresponding logarithmic function. All right. So first property, log base b of 1. And again, I tend to like to put grouping symbols around the 1. All right, b to the what is 1. B to the 0 is 1. That's true for any nice base b. All right, so this is the log form. Here's the corresponding zigzag, the exponential form. B to the 0 is 1. Now, we're especially curious about what happens when the base b is our favorite base, e. Well, if log base b of 1 is 0 in general, then in particular, log base e of 1 is 0. And remember, instead of log base e, we write ln. So it's good to know that ln of 1 is 0. That's a good thing to memorize. So this last column here is a column that you should memorize. And then just remember that these statements here will extend to other nice bases, not just e. All right, next one. For any nice base b, what is log base b of b? B to the what is b? Well, a horse is a horse. B to the first is b to the first, right? So the log here is 1. 1 is the exponent that takes you from b to itself. In particular, log base e of e is 1. In other words, ln of e is 1. That's what you really memorize. How about log base b of b to the x? B to the what is b to the x. Again, it's another horse is a horse problem. B to the x is b to the x. This is like a special case of this where x is 1, right? Okay, so in the special case where the base is e, log base e of e to the x is x. Or, in other words, ln of e to the x is x. And this is an example of an inverse property where these two functions undo each other. They're inverses. So the x here becomes the x here. The composition of these guys is the identity. Now, there's another inverse property that we need to look at. It's this over here. B to the log base b of x. So here we're logging first and then doing the exponential function. And once again, the answer is going to be x. But we do have a condition here. It turns out that we only take logs of positive numbers. We'll talk about this. So this property only works if x is positive. We only take logs of positive values. We'll discuss that. All right. Now, what's a way of seeing that? Okay, well, log base b of x, that's the exponent that takes us from b to x, right? So think of the box method, right? B to the what is x. So instead of this, imagine the box, right? Well, b to the what is x. You're going to get the same number up there. So imagine replacing this with the box. And you're basically saying the same thing over and over again. In the special case where the base is e, e to the log base e of x is x. Or e to the ln of x is x. Again, these two functions undo each other. Okay, so I'll take up the markup tool here. All right. Remember, we like to put parentheses normally around the arguments. Ln of 1 is 0. Ln of e is 1. Ln of e to the x is x. and e to the ln of x is x. You should memorize these four. Ln of 1 is 0, ln of e is 1, ln of e to the x is x, also e to the ln of x is x, provided that x is positive. And you extend these to logarithms in general, where the base is any nice base, not just e. So these work if the base b is 2, 3, 4, 10, and of course e, and so forth. Now I'd like to discuss this restriction a bit more. Why do we only take logs of positive values? All right, the log of a non-positive number is not real. That's the problem. It's a problem of keeping it real. So in this class, we only take logs of positive real numbers. Now, I know we've dealt with I before, but we're never going to mix imaginary numbers and logs. You do that later in a complex variables class, which electrical engineers do take. All right, example. Log base 2 of 1 is not real. Try the box method. Log base 2 of negative 1 is what? Can we get a real number to fill in that box? Well, does 2 to a real number equal negative 1? Look at this. Does 2 to a real number equal negative 1? No. Nobody does that. Nobody does that. So this thing here has no real solution for the box. So what we say is that log base 2 of negative 1 is either undefined or not real. Actually, you could say that an imaginary number could correspond to this, but we're going to keep it real. And this thing is not real. Also, observe that it's a range issue here. Observe that negative 1 is not in the range of the 2 to the x function, right? Only positive numbers are in the range of the 2 to the x function, so this thing has no real solution. That's what I mentioned over here. Similarly, how about log base 2 of 0? Well, again, that's not real, because 2 to the what is 0. 2 to the what is 0. Well, I can't fill in that box, not even with an imaginary number. So log base 2 of 0 is not real. In fact, more so than before, it's undefined. Log base 2 of 0 is just a mess. So we can take log base 2 of any positive number, but we do not take log base 2 of a negative number or 0. And that's true for all logarithms. Okay, once again, the last two properties are called inverse properties. These functions undo each other. The x's here become the x's there. All right. So next, let's discuss these inverse properties in more detail. All right. So let f of x be b to the x, where b is a nice base, like e. And f inverse of x, it turns out to be the corresponding logarithm, log base b of x. So these two guys are inverses of each other. They undo each other. And we saw that in those two rules up here, right? They undo each other, just like the cube root of x cubed was plain old x. They undo each other. All right. So what do we know about inverse functions? Remember that the graph of y equals e to the x was that j curve, right? Because the base here was greater than 1, and the graph of y equals e to the x is going to give us this j curve. Now, if we're going to graph the inverse function, what do we do? Remember, the line of reflection is given by y equals x. It was this over here, remember? Y equals x. When you invert this guy over, this was a homework problem, you get this. Here's a nicer picture. All right, so here's the graph of y equals e to the x. It's the j curve, right? Y equals x, the dashed line here, not an asymptote, but it's a line of reflection. When we reflect the red graph, we get the blue graph over here. This is the graph of y equals ln of x. It's kind of like a square root concave down hook, except it does not start at the origin, and there's actually a VA there. Speaking of which, notice that the red graph, y equals e to the x, has an HA, a horizontal asymptote, while the graph of y equals ln of x, the blue graph, has a VA, a vertical asymptote. What else do we notice? Well, remember, if the point AB lies on the original graph, the point BA lies on the new inverse graph. So if the point 0, 1 is a y-intercept on the red graph here, then the point 1, 0 is an x-intercept on the blue graph here. AB goes to BA. So the intercepts basically switch over. Okay, now what else will switch over? Remember that for a pair of inverse functions, we're switching inputs and outputs, the set of inputs and the set of outputs, which means that the domain of one becomes the range of the other, and vice versa. All right, so let's remind ourselves. For the e to the x function, right? For the e to the x function, what was the domain for this? Well, think x coordinates. We pick up every real number as an x coordinate on this j graph. So the domain for the e to the x function is all real numbers. What about the range? Well, the range is y. It's only the positive reals. We only pick up the positive real numbers as the y coordinates. So once again, the domain for the e to the x function is r, all real numbers. The range is the positive reals, the open interval from 0 off to infinity. And again, the x-axis is a horizontal axis. Now, when we consider the inverse function, y equals ln of x, remember, the domain here is the range here is the domain here. The domain for the natural log function is the positive reals. Notice the only x-coordinates we pick up on the graph are the positive reals. The range is the set of all reals. All real numbers work as y-coordinates. These y-coordinates do go off towards infinity, kind of like square root. There's no HA for this guy. However, there is a VA for the blue graph. So the HA for the red graph, the original function, becomes a VA for the blue graph, the new inverse function. Remember, the domain of one becomes the range of the other, and HAs and VAs basically switch here. All right, next up, let's talk transformations. Hey, these are functions, so we have the same old rules. All right, let's consider f of x or y equals ln of x minus 3, this transformed log guy. All right, let's write the domain of this in interval form. Remember, this is real if and only if the argument here, x minus 3, is positive. We only take logs of positive values, but we can take the log of any positive value. So, to find the domain for this whole thing is real if and only if the argument x minus 3 is strictly positive. It cannot be 0. Add 3 to both sides, x is greater than 3. So the domain in interval form looks like this, the set of all real numbers that are greater than 3. That's an open parens, not a bracket. And that makes sense because let's take a look at Desmos. All right, so here's the graph of y equals ln of x, that hook. All right, notice the y-axis is a VA, x equals 0 is the equation. Let's graph y equals ln of x minus 3. When we substitute x with x minus 3, remember we translate the red graph to the right by 3 units over to the green graph. By the way, this is a horizontal translation. It may not look like it because I think our eyes are tempted to look for perpendiculars here, but this is a horizontal translation of the original. Think horizontally. 3 units, 3 units, 3 units, 3 units. I know our eyes have a hard time seeing that, but we do have a 3-unit gap horizontally between the two graphs. So what's the domain for this transformed function? Well, the new VA, by the way, is at x equals 3. The purple line is the new VA for the green graph. What are the x coordinates we pick up on the green graph? All real numbers strictly greater than 3. All real numbers strictly greater than 3. The range, again, is all reals. All right, so the domain, we've confirmed it. All right, and here's another version of this picture over here. Remember, we like to put dashed lines as asymptotes. Red graph, VA here, 3 units to the right. The blue graph, VA here. The domain is also shifted by 3 units. All right, so that is section 3.2. I'll see you next time.